I can first. Yeah, today we are glad to feature Babak Rahmani, an exponential speaker from Microsoft Research, Cambridge, UK, that who has focused on optimizing language models for efficient performance and enhance their reasoning ability. Yeah. Yeah, he earned his PhD from the EE department of EPFL Switzerland. Babak is Maria Career Research Fellow with his work appearing in various awards such as Nature, Science, Nature, Machine Intelligence, and Neurips. I think Babak can study presentation. Yeah.
Yep. Thank you very much for the introduction, and I'll be sharing my slides. Can you see my slides? So let's get started. I'm very happy today to talk to you about a recent work. Please feel free to stop me anywhere during the talk and ask your questions. And yeah, so today I'll be talking to you about implicit language models. In particularly, we gonna see what are these implicit language models, and we know how are different with the state-of-the-art language models that people use in production. So we know that those models are usually mostly, safe to say, based on transformer architecture. What we propose in our work is a language model that's qualitatively different. So these qualitative differences would produce extra features for the model, and that particular features are basically these models are finite state machine language models in the sense that they can track a state. I'll be talking why tracking the state is important, but generally we show that these language models produce more expressivity. And as we know from literature, this extra expressivity, then you will be diminishing some other aspects. And for example, those you cannot train these models in parallel. That's what we know from RNNs. I was talking about how these models compare to RNNs. But we provide a solution in order to keep the expressivity and allow parallel training, and with that we can scale these models to the scale that is required for any language understanding. On the other hand, these models are interesting because if you were asking like some time ago that would these big companies using language models would ever use any iterative or recursive models, and the question would be no, because this is very expensive. But we've seen recently that this is no longer the case, and a lot of companies and startups are focusing on iterative models, and that is particularly important for what we know as reasoning, right? And reasoning is safe to say that no one really have a very accurate answer of what is reasoning. Usually what people do is try to come up with some benchmarks for which we can test language models. These benchmarks ranges from puzzles, like you get questions like you swap ball 1 and 3, swap ball 3 and 5, swap ball 4 and 2, where is ball 1, or the state of the word in that puzzle. Another thing that is very important and is becoming more interesting, more popular, is code evaluation. So suppose you have a long code, right? And one very simple task in code evaluation is to track the states of variables. And in order to understand the code, that's the first principle, to know what variable what is the value of each variable during the code evaluation. And another thing is solving math problems. So we were seeing that a lot of new benchmarks coming up that require solving Olympiad maths and things like that. So all of these things people put under umbrella of reasoning. And for example, what we're seeing here is like a simple reasoning math tags on the bottom right. This is a group algebraic problem, which is basically predicting the next sequence in sequences of token. So a token is made of 5 elements, and these elements belong to S5. So then we want to predict the prefix product for the next sequence, or prefix sum and things like that. So there is a simple rule behind it, right? And if the network, if the LLM understand this rule, it should be able to predict the next token, no matter the sequence length, right? And then the question is, can LLMs learn this algorithm in principle? And let me double down on this example again. And this is the question that we ask, right? So we again, we were focusing on this as 5 permutation compositions. So it's made of 5 elements. You put them into a stack, right? And for a starter, we came up with this little example, little prompt that we explain the problem. We give a little example, and then we ask the LLM, can you predict the next element in the sequence? And yeah, and then we were it was very interesting for us to see the results. So what we're seeing is that as the number of samples in this sequence gets longer, the GPT cannot solve the task. Whereas we are seeing that O3, O1, and this was at the time we only had O1. Now you can also test on O3 from OpenAI, can solve the task up to very short sample lengths. And after that, it basically cannot solve the task. So basically, it shows that these models have not learned the algorithm behind it. And this is also interesting, is that under the hood, O3, in order to solve up to 15 samples, that's where it breaks, it requires 10 times more tokens. The process is 10 times more tokens under the hood. So this is very costly. And yeah, so these questions made us think like, what is wrong? And if you look into the literature, basically this is something that is known. So transformers are fixed steps models, right? And this having a fixed number of layers probably limits what they can express. And basically, for all of these tasks, particularly this S5 composition problem, you need to be able to track a state. So if you do that, if you can do that, then you can solve the task. And these models cannot track a state. And if they do so, they usually find shortcuts, right? So for an algorithm, there are many ways to solve an algorithm. They find shortcuts and they solve it. They do not learn the underlying task. And yeah, so this is known in the literature. This is particularly from Merrill's work in 2020 and 2024. So this evaluations based on transformers. Then there Merrill talked about like what does it take to solve these state tracking problems, right? You can transform all of this analysis into the language of com complexity classes, right? What they showed was that state space models, which we're talking more throughout this talk, and transformers belong to TC0 complexity class, which means they have a fixed number of steps, and these algorithms belonging to this task, only those which can be solved with fixed number of steps. On the other hand, there is NC1 complexity class, which require logarithmically many more layers. The algorithms that belong to the class are this S5 or A5. Mary also talks about chess problem or coding, that the example I showed you earlier, or this entity tracking, right? All of these require a notion of state, and transformers and SSMs cannot solve this task. This was particularly showed for an example of A5 in Mary's paper, which we are seeing here on the right. So it was exactly the same type of problem. We are seeing here that the question was, how many layers do you require to solve this A5 task as the sequence length increases? What we are seeing here is that Mamba and its state space model and transformers require increasingly more layer with the increasing sequence length. This is in contrast to RNNs, which can solve this task with only one layer. So, and this is something we know, that RNNs are finite state machines. So basically, they can track states. And yeah, so this paper back at the time uh, started a lot of like Twitter discussion and everything, and but if we want to kind of like wrap up to this point, we know that transformers requires increasingly more layers in order to solve this task. RNNs can solve this task with constant number of layers, but why not people using RNNs? Because they cannot be trained in parallel and you require to train them in sequential mode, whereas transformers can be trained in parallel. That's why transformers are the backbone of current language models. Then there were state space models, which first originally conjectured to be able to get all the good features of RNNs. So they require a constant number of layers to solve this task. And also, state space models can be trained in parallel due to linear state transition that is embedded in their mixer architecture. However, from Merrill's work, we now know that you require increasingly more layers in order to solve state tracking tasks. So this is existing works. What we produce in our work is the notion of implicit LLMs, which we show that they can be trained in parallel and they require constant number of layers for state tracking, solving the state tracking problem. Okay, let's get into what is an implicit status space model. So I will be talking more about state space models, but as I show towards the end is that implicit language models, you can use any core architecture as a backbone and you can make it implicit. So we tested with both Llama and state space models, and I'll talking about the results later. But basically, it's a more of a framework rather than an architecture. How does this work? So you have your sequences of tokens, right? They go through to your favorite language model and they produce an output. The difference then is that you don't stop there. You get these outputs and then feed it back to the same network. And you do so until you reach a fixed point. And that's our choice of stop criteria. So you could choose any type of stop criteria that you want, which then these models wouldn't be implicit. They could be called weight tight and things like that. But our stop criteria is based on reaching a fixed point. And the fixed point meaning that the differences, the outputs do not change within a limit. So what we're seeing here, we have two axes here. The x-axis are the token axis, whereas the y-axis is the iteration count. So we can train the models in parallel in the token axis, in the x-axis, whereas still the model is sequential in the y-axis. So this was the training framework for training implicit models, which we have the simultaneous training. And once you have your model trained, we switch to the inference mode. So you get your first token, right? And will process and only that so that it reaches a fixed point. Then you go on for the second token and so on and so forth. The reason that this model then is able to keep the same performance from coming to the training mode to the inference mode is this nonlinear transition from processing one token to another one. I will be talking why there is nonlinear transition between hidden states later, and we have a theorem about it. But just as an intuition, these two models, these two simultaneous processing and sequential processing work similarly. And this is what we call a duality between parallel and sequential framework in the implicit model. So what we're seeing here on the left is our implicit model, right? For all of the tokens are processed all at the same time. Some of them reach fixed point, some of them do not, but we will put a hard stop threshold so that whether they have reached a fixed point or they have not reached a fixed point, they should stop. So all of the in the vertical axis, all the tokens are processed at the same time. Then we compare this to sequential processing, meaning that you get your first point, you go to a fixed point, and then you process your second token. And we've shown empirically that for both a transformer backbone and a state space Mamba 2 particularly, so we've been using Mamba 2, our favorite state space model, the difference between a trained model in inference and training is below around 0.12 perplexity difference between inference and parallel training. And this shows that you can basically switch whatever your model have learned during training, particularly for generation. You are still able to use your model in inference mode sequentially. So I should say, like, this is what we observed empirically. We don't have a theorem for this to show that why there is this duality between these two modes. But our intuition here is that so there are a lot of work around fixed point models, not particularly for language, but generally, and they are known like as deep equilibrium models. In the context of these models, there is a notion called path independence, meaning that it doesn't matter which path you traverse, given an initial point and your input, you do not need to store the path or the trajectory. You can only use the fixed point. And since in the parallel mode, the tokens reach almost to similar fixed points, at inference, given a token, it doesn't matter which path it has reached. As long as for any token inference mode, you reach a fixed point, it doesn't matter where you came from. And that's what we think is the duality between these two modes. Okay, so I alluded to our empirical result for showing duality between training and inference on the pile dataset. Now it's a good time to talk about how you would go about training these models for any dataset. So in our approach, we came up with a curriculum training method, and I'll explain what that means. So basically, our training consists of two steps. One is a fixed point search, followed by something that we call a phantom gradient step. So let me backtrack a bit. So one particular issue with these models is that you need to traverse or sequentially reach a fixed point. If you were to checkpoint gradients and back propagate through all of these paths, your memory would blow up and you wouldn't be able to train basically large models, right? The trick for training these models is that you do not keep the gradients in the fixed point search. You basically do in PyTorch, which torch no grad, right? You don't follow the gradient at that step. Once you reach a fixed point, for few steps, you start keeping track of your phantom gradient. And you use the fixed point that you found in the first step as the initial point for the phantom gradient up the truth. And usually this number of phantom gradients is small. We've experimented with one and up to 4 steps. So basically, you have to store as much as 4 more activation compared to an explicit model. By explicit model, I mean a normal model that do not iterate, but basically has the same number of parameters as the implicit one, and it only outputs in one step and one forward pass. Yeah, so this is basically our training curriculum. It is made of 2 steps, and yeah, and you only back propagate through the phantom gradient steps. Okay, then maybe it's good time to explain why implicit language models, or basically implicit neural networks, implicit LLMs are RNNs. So what we are seeing here, for example, particular case of state-space models on the left is the mixer update of a state-space model, right? So you have your state transition matrix that depends on input. You have your states, H, and you have your input. And that also depends on the input. And that's the mixer state update. And there is also an output update, right? So this is a normal model. What is different in our model is basically the notion of introducing this dummy variable. If you remember from my previous schematic, is the y-axis. You have to have a y-axis, and that's our z here, which uses the superscript s to show the trace in the vertical axis. So we have this another variable, and basically it's interpolated between the two. You first find your hidden spaces, you do a forward into info for time t, and once you have that, you do a forward for z, and this will become the update rule for the implicit model. And you do so up until you reach a fixed point, and that we show it by star here. So we have a little bit of a small theorem for state-space models, particularly in the paper, which shows that if your model follows the equation 1 and 2, and once it reaches the fixed point, the function between going from the state transition from H, the previous token, to the next token is both non-linear and non-diagonal. So the proof to this is simple. I'll just explain the proof to showing that the non-diagonal state transition, and the way to show this is that you basically have to write your in fixed point definition, and then you take a gradient, and the gradient of your next hidden state at token t with respect to the gradient of the hidden state to token minus t. If you write it down, it becomes something like that. And this shows that this is a matrix that is non-diagonal. And we further prove this by plotting this Jacobian, this derivative. Right. But what we're seeing here on the left is if you take one of your trained models and computationally compute the Jacobian, that is autograd Jacobian. And what you can also use this formula, the formula Jacobian and the autograd Jacobian, the difference between the two is very small. So this shows that, and what we're seeing from the structure is that the Jacobian is indeed non-diagonal. How is it important compared to a normal state-space model? The transition from HT to HT minus 1 to HT is diagonal. And that's what makes these models of higher expressivity. Okay. Yeah, so basically that's how you would go about train a model. And that we just talked about the higher expressivity of these networks. Now it's a good time to go back to the problem of S5 that we introduced in the beginning. But we did the test of what Merrill did in their paper, and we try to compare the performances of the implicit models, implicit Mamba2 model compared to an explicit Mamba2 on the S5 problem. What we see is that an implicit model can solve this 5 problem for very long sequences while requiring only one layer. And that's the implicit in red. For example, if you have an input distribution sequence length of 64, so these are independent runs. So each point is, if your training data is made of 64 elements, 64, and each element is 5 elements, and you train with that, it requires one layer to solve it to a test accuracy of 100%. This is in contrast with an explicit model, which requires increasingly more layers. This is the mirror's work. Yeah, and it basically shows that and these implicit models of higher expressivity and become an RNN. Um, and S5 is particularly important because in the complexity classes, this is considered a very difficult problem. And there are other types of problems which all can be reduced to this 5. So basically, if you show that you can solve one of these S5 problems from this class complexity, um, uh, then yeah, so your models will become in that class. So this is for training and testing from the same distribution. And what we can do now is take one of these models, all of these models, basically there are 5 models on the left, take them and just do tests out of distribution testing on them, meaning that you just throw more longer sequences at them and then evaluate their performances. Um, what we're seeing is that an explicit model that had 60 layers, when trade up to a sequence length of 32, cannot solve basically up to 64. And it fails very quickly. Whereas an implicit model and can basically solve the task for very longer, much longer sequences. This is perhaps a good point to also note that a one layer implicit model has 16 times less parameters compared to an explicit one, what we're seeing on the left. Um, yeah, so basically this result confirms that the higher expressivity of the implicit models. We before talking about current language modeling testing, we did another experiment on what is now considered a toy reasoning data set, the cat-bobby data set. So basically, the cat-bobby data set is something. The Bobby data set is from like 2016 or something. There's cat-bobby data set from 2021. It's made of like 20 tasks, so it's a good little now reasoning type of data set. It's made of conference, one argument relation, two argument relation, three argument relation, agent motivation, pathfinding, and basic deduction, which explains like a kind of like a puzzle or text. Mice are afraid of cats, cats are afraid of wolves, and you ask a bunch of questions and a bunch of text, whether relevant or non-relevant, and then at the end you ask a question or similar tests, other type of task. And what we were interested to see from this, what we can call a toy reasoning, which allows us to compare the two models in a controlled environment, because we both have access to the task and we can control all sorts of things on them, was how do the implicit model and explicit model perform in OOD settings. And by OOD setting and the sequence length, I mean, how do they perform when you have a longer sequence? Or basically, how does the performance of the models based on differences in the sequence or a story length here? And yeah, so we're seeing that the explicit one layer almost contains its performance across different story lengths, whereas the explicit one fades for longer one. And then we can also look at the task performances for all sorts of these types of tasks. And that's what we're seeing here on the left. So basically, explicit and implicit both perform similarly on some types of tasks from indefinite knowledge or a basic conference and things like that. But there are some sorts of differences for particular tasks. Yeah, for example, that pathfinding explicit fails miserably, and two supporting fact or three supporting fact, things like that. Um, and we should also say like the implicit model still also lacks in some tasks, right? For example, it's not doing very well on the like this one, which is a basic induction, right? Um, so what we can our intuition is like it can solve those things which require a notion of state here. I should say that, so this was with one layer of explicit model and one layer of implicit model. You can imagine your base model has more layers. And if you do so, for example, the implicit model improves its performances. I don't have the plot for that, but you can improve the performances of the implicit model by adding more layers, more parameters in the core architecture. Then the same goes for the explicit model. And as you increase the explicit model sizes, then the two models kind of become similar. But this was more like a control experiment telling us like what sorts of things are important for implicit model and what sorts of things implicit is better than explicit one. And you can look at these types of tasks and get an understanding like what are they good for? What are these implicit models good for? Okay, so that after this a little bit of like toy example reasoning, we can start talking a little bit about implicit large language models or implicit LLMs. Um, yeah, so as I alluded to earlier, we were using a Llama architecture for our backbone and a Mamba 2 architecture for our backbone. And we made them implicit models. We had a suite of four sizes from small size, 130, all the way to 1.3 billion. And we used the Pi dataset and particularly the deduplicated Pi dataset from, if I'm not mistaken, Eleuther AI, which contains of 207 billion tokens. And we had a curriculum training, which I explained before, and I'll talk about later. Yeah, so these models were trained, particularly with AMD GPUs over course of 1 month. And yeah, we had a lot of fun training these models on AMD GPUs. But yeah, so maybe then I can talk about the curriculum training. So I explained that we had two steps. One is the fixed point step, and one is the phantom gradient step. And we denote it here by, for example, 4+1. So 4 means there are four fixed point steps, and one, the second numeric there, shows the phantom gradient steps. Our curriculum training contains of training the model for most of the tokens, like 70% or 80% or 10%, with using only four fixed point search steps and one phantom gradient steps. The reason for this is due to decrease the cost for training these models. And after this initial step, which we don't call them implicit model, we actually in the paper we call them they're weight type model. You do not necessarily reach a fixed point after 4 steps, 4+1 steps. So after 70%, after some processing of the tokens, then you switch all the way to increasing your fixed point searches steps and also increase your number of phantom gradient steps. And what we are seeing here is that there after certain number of token process, with the full what we call unbounded fixed point search, like 20%, 10%, there's not much difference between the two. Whereas if you do not have a long, unrestricted or unbounded fixed point search, then performance a little bit is lower than compared to when having higher number of fixed point searches. Yeah, so that's how we brought down our cost for training these models. And that's what we call our curriculum training. Now it's a good time to look at the perplexity performances of the models across different sizes. So the result showing here is that implicit uh, models outperform the explicit ones in perplexity across different scales. And this shows that these models are parameter bound. And yeah, so this is the scaling law showing here for parameter. I have to say that the scaling law for flop is not similar, right? Our models use much more flop compared to the explicit one. But if you care about having the same number of parameter, these models are optimal compared to explicit ones. Um, okay, let's move on. So once we have the perplexity, what you do after is do downstream task testing, right? I will talking showing you the big table that we have that's common now. People testing their models on all sorts of evaluation. But one particular data that I want to single out is the HELA SWAG data set, right? So this is 1 out of 7 tasks that we evaluate our model on. And this is basically a sentence continuation type of a task. And this is the data set that we observed that their models perform really well compared to the baseline and explicit ones. Uh, and particularly the advantage of making your model implicit for Llama turns to be much more compared to Mamba 2. So the differences between a baseline Mamba 2 and implicit Mamba 2 is lower than the difference between an implicit transformer and implicit llama and a baseline llama. And yeah, so this is what one task that can be observed constant improvement across all tasks, across all sizes for the implicit model. And yeah, obviously we also evaluated on all these 7 benchmarks, right? Um, what we see, we established that we got better perplexities compared to the baseline models. And yeah, for the perplexity, I also should add that we observed that the implicit state space models, not true for the implicit llama. When you increase your context length, the perplexity remained more constant compared to a Mamba 2 or other state-space models, particularly like XLSTM paper. So you have this graph of perplexity per token, and you increase. So we went up to a 16K token length, sequence length, and we observed that the perplexity of implicit Mamba 2 remains constant, whereas the Mamba 2, the perplexity gets larger and larger. So that we observed a better perplexity, and then on the downstream task, what we observed across all sizes, I only show 2 model sizes here, is that compared to the so we compared to the baseline llama, the one that we train in-house, so that's the one showing in Dagger, and the one that is available publicly. Compared to both, we always across all tasks we improve few points in percent improvement across all tasks. Again, the improvement is more pronounced across some tasks like HelaSwag or Pika or RKey, and is less significant across other tasks, but the improvement is always there. This is in contrast to the Mamba 2 results. Again, for Mamba 2, we observe that, so I think it's more fair comparison. Just to be super fair, we presented the results both from Mamba 2 paper and the Mamba 2 that we trained with our own data sets and our own pipeline and everything. And what we notice here that our model outperforms compared to the Mamba 2 that we train in-house. And it across particularly some task, not all of it. To the two tasks that we did not, uh, we were not able to beat compared to the explicit one is the, if you've noticed here, is the Vino Grande and open book question answering. And was not the case for Llama. And we think these two tasks do not require state tracking that much. They require knowledge that these Mamba implicit Mambas were somehow forgetting compared to explicit one. Whereas except for these two tasks, across the other ones, we again see the improvement compared to the explicit one. Uh, Yeah, so this is our downstream evaluation, and then we can come
I think
to,
there are two questions in the chat. Maybe you can
yeah, okay.
answer them first. Yeah, thank you very much.
It looks like the numbers of layers needed for transformers to stack state really only grows as log L. Is this really such a big problem? Yeah, number of layers for transformer to track state. It depends on your task, right? In the cat Bobby dataset, right, we show that up to 3, 4 explicit, the normal model, it reaches the performance of the implicit one. Whereas in other tasks, right, initially we were showing the GPT-4o or even o1, right? And they were not able. So how many layers do they have for? I don't know. Uh, but they were not able to solve the S5 problem up until 15 elements, right? And in order to be able to solve S5, then you need to have logarithmically more layers, right? Yeah, so it depends on really on your task and what you want. But the fact that even the large models that people are using in production cannot solve this task shows that one cannot always try to increase the number of layers, and it's better maybe to find another solution to solve this.
No, that's a great answer. Just checking. If 4.0 were fine-tuned on the S5 task, it almost surely would be able to solve it for long sequence lengths, right?
If the 4.0,
Yeah, if it like because it has like if you just compare with Merrill's graph, like you only need like 4 transformer layers to solve like a length 15 S5 state tracking task. So maybe the issue there is that like Merrill is explicitly training on the S5 task, whereas 4.0 is
yeah,
not.
yeah. But again, Merrill shows theoretically that you need more layers, right? Of course, if you fine tune an S5 with a particular sequence length, that what we also showed for the uh, Mamba model in the S5, this here, right? If it shows that you, even for 32, you require 16 layers, and once you go OOD with 64, it fails. So you can imagine that you can increase this more and more and more, but there is at some point it just fails, right? Because theoretically it should fail. Yeah, it depends how long, how many, yeah, sequence length is important, but we are more interested in solving the problem rather than increasing layer. There was another question which I can get to. Oops, I lose the. Is the unbounded phase be 24 steps, or is there a different unbounded phase. No, unbounded is 24 steps. Unbounded means we put a threshold, a maximum number, but unbounded in the sense that they need to reach a fixed point. This is in contrast with 4, which would never reach a fixed point in 4 steps.
Did you always observe reaching a fixed point within 24 steps? Like you just didn't need more than 24?
Yeah. You could, it depends on your, so the threshold that you put, we were going with 0.05, something around like 10 to minus 2, and we always observe that they reach a fixed point. Okay. And then let's do these test time compute performances, or should we call them test time compute? So there was another paper talking about a concurrent paper, test time compute with implicit models. So what I am plotting here is the downstream task performances of the implicit models, implicit Mamba 2 and implicit Llama, which I just showed in the previous table, based on the iteration of the implicit model. So what you could do is that you project the iteration count of these models out after certain number of steps, 1, 2, 4, 8, 16, right? This is possible due to the fact that the size across these iterations are the same. So you can just use your header, language model head, and project it out. And if you do so, we see that these performances of the models across this task increase until a point where they plateau, right? For implicit Mamba 2, we train the model with 24 iteration, right? For transformer, we use 32. If you're interested why we will use 32, because the eigenvalue ranges of a Mamba 2 is closer to unity, is smaller compared to a transformer, and that is because of the structure that Mamba 2 has on the state transition matrix. It needs to be, it's already been bounded. So the overall, the spectrum range of, the eigenvalue ranges of Mamba 2 is small, so it reaches a fixed point quickly or sooner compared to a transformer which does not have this state transition constraint. So that's why we observed that we require 32 iterations for the implicit one to reach a fixed point. But the point I'm trying to make here is that what we're seeing here after center number of iteration, the performance of the model is kind of like plateauing, right? This is good in some sense that they're not as computationally intensive as you would imagine them, right? You could imagine them that they require same number of iterations as you tested them, trained them for, but we kind of like seeing that they kind of plateau after center number of iterations. And yeah, this is in some sense a test time compute, meaning that it at least is adaptive. Depending on different tasks, you could always stop early. Or in some cases, you might want to continue iterating compared to the iteration that you use for training. But in the sense of current literature that we call it something, a test time compute, your test time number of step iterations a test should be much larger and you gain you gain more out of that. So this is really not a test time compute. That was my point I was trying to make here. And yeah, so what we did in our work was theoretically showing that implicit SSMs are RNNs. We lifted the illusion of space models in Merrill's work. We came up with scalable implicit training up to model size of 1.3, and we also observed improved state tracking in the downstream tasks. And the next step for the work is now really trying to make them test time compute, meaning that we can take these models and try to take them to really self-iterate something that is useful, so that you see gains from iterating the models more and more. One other thing that it's important to note is that they are self-iterated in latent space rather than in token space. So all the sorts of work that people are thinking about, like the coconut or this implicit chain of thought and things like that, you can basically do with these types of models. And yeah, and then people can think about maybe trying RL with these types of models, and yeah, things like that. Yeah, and that concludes my talk. But happy to take more questions if there are any.
Yeah, I think I have one question that first that because you show that the sequential and the parallel are maybe similar, but it seems that the llama have a larger discrepancy in comparison with member. Yeah, what do you have some idea about this thing?
Sorry, there was a hang. Could you repeat your question? I didn't get it.
It just means that because that you show that you can train with parallel and test with sequential, and you show the small discrepancy in the perplexity, but it seems that llama has a larger discrepancy. Yeah.
Yeah, I think it's the fact that I alluded to the eigenvalue ranges of the Mamba and the Llama. So it is usually more difficult for the transformer to reach a fixed point. So meaning that if we were to train, so that 32, we use 32 iteration to reach a fixed point, right? And we also set a higher stop criteria, a larger one. So it really didn't reach a fixed point. And if we were to make it really reach a fixed point, we should have like increased the number of 32 number of iteration to something like more. So our models in this bit were not really close to a fixed point. They were almost a fixed point. I think the difference comes from that. And generally, Llama models have, we observed because of that eigenvalue ranges, they have a harder time to reach a fixed point. Whereas Mamba models, they can reach a fixed point very nicely to eigenvalue ranges. So I think this discrepancy comes from that.
I see. Yeah.
And the fact that they are not path independent. So if we would have reached a fixed point, it would have been similar, the result.
Yeah, I think shall we have a question? Yeah, maybe you can directly unmute yourself and ask it.
Yeah, thanks for a really interesting talk. I mean, one question is like, if you're able to get convergence to the fixed point in 24 iterations always, why not just train an explicit model with 24 layers? Like, what would be the difference?
So the 24 explicit model with 24 layers means 24 more parameters, right? So if you could try to, so there are two notions, right? Isoparam or isoflop. What you're alluding to is you get the explicit model and try to make it deeper so the number of flops become the same, but you are using more parameters there.
Right. But is there a reason why should we prefer isoparameter over isoflop? Because it would seem that isoflop would actually matter more for runtime in practice.
Well, yeah, it depends on your application, right? So isoflop, yeah, exactly. It matters more for runtime and inference. But I think there are certain tasks, and also looking at the current direction that the research going within reasoning, that you really need these flops, right? Whether you want to iteratively solve something, you're basically getting an explicit model and trying to get the output and put it input and basically increasingly adding more flops, or you want to have an architecture which has this as a core rather than a post-training approach. So to answer your question, it depends on your application. Some applications requires these flops to be more in order to reach a good performance and be able to solve the task. But yes, sure. These things. I like the way that we say it in the paper. These are good for text in the long tail, and by that we mean for tasks that require this property. If you were to use these models for tasks that do not require state tracking or reasoning and things like that, you shouldn't be using these things.
That makes a lot of sense. Thank you.
Yeah.
Yeah, I think that is
Okay, I hope you can see me. I'm on my phone, sorry. So I think just to add on this, I think it's also a bit about adaptivity, or I think that is actually the crucial point. If you just had like 24 fixed layers, the model could not adapt to the difficulty of the task, and that's what we usually want, or that we now want in these type of reasoning models, that we can we get a more difficult task, we just spend more iterations to spend more test time compute, and that would not be possible with a fixed sized like language model of 24 layers, for example.
Yeah,
but true. I wanted to, yeah. So that's also a bit what I got from Jonas Gepping's talk a few weeks ago, and I think you're obviously you're tackling the problem a bit from a different perspective. But I wonder if you have studied this other work and roughly can kind of say a bit how you think the focus is different, or maybe you also mentioned it already, but so just what's your perception on how these works, yours and theirs, like contribute in their own ways, so that we understand a bit better what to look for where?
Yeah. Yeah, that's a good question. So basically our angle in our work was more, it all started with the state space models, right? And all sorts of like state space models are RNNs. And we have a theorem to show that. We didn't have time/capacity to show that for the llama models, right? We don't have a proof for that. And it's only empirical on that aspect. Compared to you, I also listened to Johannes' work. So I think the method is very similar. We use phantom gradient, whereas they use this random number of iterations. So what they do is that they sample, as far as I understand, a maximum number of threshold from a Poisson distribution, and the models can take that many steps. They do back propagation, truncated back propagation, which is similar to phantom gradient. Whereas we see that phantom gradient is more stable. In Ioanna's work, there are a number of like issues with instability. That depends a lot on initialization and things like that. And we were quite happy that we never saw any instability issue, never for Mamba 2 models. And I think also very rarely for the Llama models, except like we were using same number of iteration as the Mambas, and we didn't reach the fixed point ranges that we wanted to. Otherwise, we'd never see any instability. And I think that comes from this using the phantom gradient part. In terms of memory consumption, we use a limited number of steps for gradient checkpointing, so it's very similar. Johannes managed to train a larger model, up to 3 billion, if I'm not mistaken. And we also have like this test time computing, although I think I have a different opinion on that, in the sense that, as I mentioned, you need to see the gains that this extra computation would bring you if you train a model with the same number of iteration, and then you see that at test time, you see the same number of you see the same performance at that number of iteration that you train a model with, that's not really a test time. So from the llama part, similar. Yes, we have a different angle on the state space models and RNNs.
Okay, thank you.
Yeah, and I was wondering, have you tried that, for example, train with 4 steps and maybe test with more than 4 steps? Yeah, because I think that based on the past independent series, they say that it can generalize to deeper layers during the test time.
Yes, so your question is like, because we also had like 4+1 models, right? And you said like use these 4+1 models that train with 4 and +1 and then test it with larger number of iteration.
Yeah, that's right.
So we noticed that the 4+1s, they do not reach a fixed point during training, but at test time, if you iterate them more, they reach a fixed point. The performances of those compared to the ones which you really find a fixed point during training is lower. So this is very important that during training, you really observe the fixed point for test performances that you expect to get. But the improvement of using a non-fixed point model and going to test time was minimal.
I see.
And if it didn't really reach a fixed point during training, you cannot expect extra computation would bring you any significant test time gains.
Yeah, and I think that in a few years ago in your talk that when they trying to do similar thing, they do not maybe fix the iteration number during training. Instead, they choose to maybe sample from a distribution. Yeah, so that I'm not sure whether it will be helpful. Yeah.
Actually, I can maybe talk about that. I think that that's very smart to do that, because if you compare these works to the large works around deep equilibrium models, they use this random number of iteration for training the model, and that actually the work of Zico, Coulter on a deep equilibrium model, they show that encourages path independence. So one of the techniques to encourage that force models to do that is to randomly choose a maximum number of iteration during training. And that is smart. I think some of the advantages they see, they also mentioned about path independence in a paper, is coming particularly because of that.
Yeah, I think that's right. Because the training, even with the DQ, the training of the forward is still very expensive.
Yeah.
Yeah, I think, shall we have a more question? Yeah.
Yeah, no, that was super interesting comparison with Jonas Guypen's work. And one thing I was curious about, like, I guess one of the bigger differences was you were using the phantom gradient, whereas they were using like just truncated backprop through sequentially. But
Yeah.
did you choose the lambda parameter for the phantom gradients?
Yes, we did it a little bit of experiment, not very exhaustive search over the lambda parameter for the phantom gradient. So you maybe like this phantom gradient, the lambda parameter and the number of iteration that you do for the phantom gradient, they kind of like relate to one another. A smaller lambda, you need larger number of steps, and vice versa, because it's approximation to the true gradient that you would get. We across for the language models, we use a lambda parameter like 0.8, 0.85. We didn't see, we didn't really we didn't go down on that, particularly because if we were to do that, we needed to increase the number of phantom gradient steps, and then that would blow up the memory during training.
If lambda were equal to 1, would your phantom gradients have been the same as Guipeng's just truncated gradient?
Yeah. Yeah. So
And
basic update rule, if you put it 1, it becomes truncated backpropagation.
I see. And do you think the fact like well do you think it was the lambda parameter that led your training to not have stability issues, or
Yeah.
could you comment? You believe that's the reason?
Yeah. So if you the phantom gradient paper, they say that like it makes the path smooth, right? It's kind of like averaging over the outputs that you have, the iterates.
Super cool. Thank you.
Maybe if we're discussing the training perspective a bit, we can have like another question on that. So
Yeah.
basically, if the question is a bit of, to me, it seems like it's a bit of a trade-off. Either you get more accurate gradients and you can converge faster in your training steps, or you spend less time, you get more noisy gradients, but then potentially you're like, because the gradients are more noisy, you would take more like trade SGD steps to converge.
Yeah.
Did you
Yeah.
think about this a bit, or like ablate this, or like how would one cope with this situation?
So sorry, your question was like if you chose a smaller. Oh, do you mean for? So sorry, can you repeat your question? I missed it.
Yeah, of course. I'm also just wrapping my head around it. So essentially, you have the trade-off in the best case. The cleanest gradient is probably if you backprop through the full iteration.
Yeah.
And the noisiest gradient is if you spend the least compute in the backprop and you just do once.
Yeah.
But so from that perspective, you would want to do as little backprop as possible.
Yeah.
But if you do a little less backprop because of the noisy gradients, like the training across like number of token budget would take probably longer because you have noisy gradients. So there's this trade-off between how much compute do I spend in the backward, like to get a clean gradient, or how much compute do I spend to get, or versus how much compute do I need to spend in order to reduce the training or loss in training time, basically. Did you think about this a bit more, or did you just?
Yeah, we observed that, right? So if you look at the perplexity of the validation that you track during training, we see that as soon as you switch, so we were using like 4 steps of fixed point plus 1 step of gradient. This is bad because of 2 things. One is like you are with 4 steps don't reach a fixed point, and that phantom gradient step is only 1. That's super bad. Your gradient is not very accurate, and your bad gradients are noisy, right? As soon as you switch to the unbounded step, meaning that increasing both the number of iteration and number of self-iteration, your gradients become more accurate, less noisy, and you go quicker on the perplexity. You go down much quicker on the perplexity. And this alone shows like, yeah. So we observed it. We did not really try to come up with the best combination of how many number of self-iteration for the fixed point is required, what is the lambda parameter, or what is the number of steps. But we observed this in kind of like a hindsight.
Okay.
Does that
So
make sense?
because I guess, yeah, I guess there's some kind of Pareto optimal frontier or whatever where you can get the best trade of the fastest reduction versus compute budget or flops or wall clog or whatever.
Yeah.
But yeah, okay, nice.
Looking more closely at figure 11, like for this conversation, it does look like there were bits in the bounded phase 4+1 where there were like some instabilities in training with like blowups and stuff, or
No. It's because issues with the AMD, they would just constantly hang, and we have to restart multiple times. And then it always restart was like from a closer previous checkpoints. We did see instabilities, and that's actually in the appendix of the paper. When that particular graph that you're using, you are referring to, and that was one thing that we observe is that if we were to train a model with lower number of effective tokens, so we trained generally our models with 1 million tokens per step. That for that particular plot, we were using 500,000, and that resulted in some instability. It and only that plot, that run, that we observed those instabilities. Yeah. So, but generally, the only instabilities that we were seeing was because of like all the hangs that we're getting from the GPU hangs and things like that. Otherwise, once we fix the we use a larger number of effective tokens, batch size. No, we did not see any major instability issues.
You're saying large batch size is important for training things. Okay. How large a batch size was
Yeah, so
needed?
1 million. So that number was from GPT-3 paper, right? They for their larger models, they use an effective batch size of 1 million, right? So it's a sequence length of 2048 times yeah, a million. So that number came from GPT-3 paper.
Got it. Thank you.
Yeah, I think there's no more questions, and we can stop here today. Yeah, thank you very much for Babak's talk. Yeah, I think that the implicit model will be an interesting direction for future. Yeah, especially that one we consider about latent reasoning or maybe more reasoning model. Yeah, thank you very much. Yeah.